You know the future of transportation we're always hearing about? It's all connected. We're talking cars talking to other cars, cars talking to the traffic lights. It all sounds amazing. Safer roads, maybe even the end of traffic jams. But here's the thing. This new digital highway has a pretty serious dark side, a whole world of hidden vulnerabilities that could turn our smartest cars into a huge problem. And it really all starts with one simple, kind of chilling question.
Just picture it. You're in a self-driving car, just cruising along. It's constantly getting updates from every other car on the road, telling it exactly where they are and what they're doing. But what if some of those cars are lying? What if that car up ahead isn't really there at all? And look, this isn't some sci-fi movie plot. This is the absolute central security challenge for the entire next generation of vehicles.
Okay, so to understand the solution these researchers came up with, we first have to get our heads around why this is such a uniquely tough problem to solve. And it really all comes down to one thing. Our targets, well, they just won't stay still. Let's think about it like this. Securing your Wi-Fi at home, that's kind of like being a security guard for a building. You know where the doors are, you know where the windows are. The connections are stable. But trying to secure a network of cars on a highway, that's like trying to guard a high-speed Formula One race where the track is constantly changing. The cars are moving, the connections between them are blinking in and out of existence. Your classic, old-school security just can't handle that chaos.
The tech making all this possible is called a Vehicular Communication Network, or a VCN. You can think of it as the digital nervous system for our future roads. And of course, it's the exact system that attackers are trying to exploit.
And this is where we hit the real snag. To teach an AI to spot these kinds of attacks, you have to train it on good, realistic data. But for years, researchers were stuck using datasets that were built for those static, building-like networks. They were missing all the crucial stuff, the physics of the real world. Things like speed, mobility, the constantly changing distances, and that relationship between space and time. It's like trying to teach a 747 pilot how to fly using a driver's ed manual from high school. It just doesn't work.
Because of this massive data gap, a whole new breed of cyber attack popped up, specifically designed to exploit the unique physics of cars on a road. So let's meet these ghosts in the machine.
First up, we have position spoofing. This is the most direct lie a car can tell. A malicious vehicle just starts broadcasting that it's somewhere it physically is not. It could make itself look like it teleported a mile down the road in a split second, creating a digital ghost car that completely defies the laws of physics and could cause other cars to slam on their brakes or swerve for absolutely no reason. Then you've got the Sybil attack, which is, honestly, even sneakier. This is where one single bad guy car pretends to be dozens, maybe even hundreds of cars, all at once. It can literally create a phantom traffic jam out of thin air, tricking the whole system into rerouting all the real traffic and causing actual gridlock by making everyone avoid a perfectly empty road.
And finally, there's the really wild one, the wormhole attack. For this, you need two attackers working together. They create a secret, high-speed digital tunnel between two different points on the road. A message from a car miles away gets instantly zapped through this tunnel, making it seem like that car is right next to you. They're not just messing with space anymore, they're manipulating time itself.
So you've got these digital ghosts, these phantom traffic jams. How in the world do you catch them? Well, it's pretty clear an old trap isn't going to work on a new kind of threat. You've got to build a much smarter one.
The researchers behind this work knew they had to just throw out the old playbook. They couldn't use that old, broken data, so they started from scratch. They built this incredibly sophisticated simulation, a true digital twin of a real city, with realistic traffic simulators and network simulators, to create the perfect high-fidelity training ground for their AI defender.
And when you look at the difference between the old way and the new way, wow, it is night and day. Those traditional datasets had zero concept of mobility. They were totally blind to the physics of a moving car. But this new dataset, it's built from the ground up with that physical reality baked right into its core. So what are these secret ingredients? Well, it's not just about where a car is right now. It's about things like the rate of distance change between two cars. It's about the communication patterns between them. And it's about adding real-world context, like a car's historical maximum speed, what they call Vmax. An AI that has access to all this data doesn't just see where a car is, it has a deep understanding of where a car should be. Okay, so with this super rich, incredibly realistic training ground all set up, it was finally time. Time to let the AI take the wheel and see if it could actually spot the liars out there on the digital road. So the team basically set up a competition. They unleashed a whole suite of different machine learning models.
They tried some simpler ones, but they also throw in heavy hitters like random forest, which you can think of as getting a whole committee of AI experts together to vote on whether something looks suspicious. They wanted to see who was best at telling the difference between normal driving and a full-blown cyber attack.
And the results, they were just stunningly clear. To grade the AIs, they used something called an F1 macro score. All you need to know is that it's a really reliable way to measure how well an AI can find bad guys without constantly flagging innocent drivers. And that random forest model, the committee of experts, it didn't just win, it absolutely crushed the test. The simpler models really struggled to keep up.
And that brings us to the hero number of this whole story, 99.8%. Just let that sink in for a second. Trained on this new context-aware data, the AI achieved virtually perfect accuracy. And we're not just talking about spotting obvious, clumsy hacks. This means the system could reliably tell the difference between a malicious ghost car and a real driver who just had to make a sudden but totally legitimate sharp turn. That's the level of precision you have to have for a system we can actually trust on our roads.
So what does all this mean for the future? I mean, this is about way more than just clever data and cool algorithms. This is about paving the way for a transportation system that we can fundamentally trust.
You know, the researchers themselves put it perfectly. They said their work addresses a critical gap. By completely redefining the problem and building a data set that actually mirrors the real world, they've unlocked the potential for security systems that are genuinely incredibly accurate. So when you trace the whole journey, the story is so clear. It started with a huge problem. Old security just couldn't handle moving targets. The innovation was a brand new data set built for a world in constant motion. The proof was that near-perfect AI detection rate. And the future this makes possible, it's one where technologies like self-driving cars are built on a foundation of safety we can actually count on.
So our cars are definitely getting smarter. The big question is, can our security get smart enough to keep up? Well, this research proves that yes, it absolutely can be. But it also leaves us with a critical mission. As our cars accelerate into the future, our security can't just keep pace, it has to be leading the way. Because on the digital roads of tomorrow, trust isn't just a nice feature to have, it's everything.